So let us now get into a discussion of these two terms, precision and accuracy. Now, in everyday language, people tend to use these two terms as if they mean the same thing. However, in the sciences, where you're taking measurements, these are actually two different terms. All right, so let's define what we mean first by the word precision. Precision refers to how closely repeated measurements approach one another. All right, so that's what precision is. So for example, if I were to give each of you the task of measuring, let's say, the length of a desk using a meter rule, and each person take their measurements and record their value, then how close these values are to each other would be a reflection of how precise the measurements are. Now, accuracy means something different. Accuracy refers to the closeness of measurements to what is referred to as the true or accepted value. All right? So that's the difference between precision and accuracy. Precision refers to how closely repeated measurements are to each other, while accuracy refers to how close measurements are to the true value. And just to illustrate what we mean by these terms, we're going to use the analogy of a dartboard and people or somebody trying to throw darts at the board. And the aim, of course, is to hit the bullseye, the middle. So the one to the extreme left here, right? So let me just say this before I move on to the actual examples here. So basically, each attempt at throwing a dart is basically representing a measurement, and the bullseye represent the true value, all right? So in this case, to the extreme left, you see that this person, when he threw or she threw the darts to the dartboard, the darts are all over the place. They're far from each other, and they're far from the bullseye, right? So this is basically reflecting a situation of low accuracy and low precision. In this case, B, where this person threw the darts on the dartboard, and they all end up pretty close to each other, but far away from the bullseye. So basically, these measurements are close to each other, but they are far from the bullseye, which represents the accurate value. So this represents a situation of low accuracy because it's far from the bullseye, but high precision because these values are close to each other. All right. And then here, in this case for C, the darts are relatively close to the middle, but they're kind of spread out from each other, all right? So this represents a situation of relatively high accuracy, but the precision is relatively low. And then this, of course, is what we try to aim for whenever we're measuring anything, right? Where all the darts are at the center. So this represents basically a situation of high accuracy and high precision. And what we try to do whenever we're measuring anything is basically work towards achieving high precision in our measurements, and hopefully that would represent also high accuracy, even though they're not necessarily the same as seen in these examples. And that could be due to several factors. There could be something wrong with the instrument, or it could be a situation where the person who's working the instrument is making a very consistent error where they're getting the values close to each other, but because of some error on their part, the values are not close to the true value. All right, so I hope that clarifies the difference between these two terms. All right, now, as stated here, we can never know with absolute certainty whether or not the measurement we make is accurate. So, right, so 100% certainty in accuracy of measurements is simply not achievable. And it asks the question, why not? And I would say that the main reason why that is the case is because the act of measuring anything is a human act, and the instruments are made by humans, so therefore there's always the risk of some inaccuracy when it comes to making any measurements. Of course, as scientists, we try to avoid that. We try to be as accurate as possible, but we simply cannot achieve 100% accuracy in any measurements, right? So what we do is that we make repeated measurements pretty much of the same thing, and we strive for high precision. And hopefully, if the precision is high, then the accuracy would be high. All right. But as we said before, that is not always true, right? But that's true in most cases where good precision represents or implies good accuracy. Now, how do we reflect the level of precision in a measured value? Well, we do that by looking at the number of what we call significant figures in an expressed measured value, right? So as stated here, we do not want to claim more precision in our work than we actually obtain, all right? As we said before, measured values are at best estimates based on the type of instruments used, based on the experimenter, and so on. So the concept of significant figure is a convention that is observed so that we reflect our measurements to the correct level of precision, all right? And what we'll find here, or what you're going to see here, is that the number of significant figures is basically a reflection of the level of precision of our particular measurement. So here's an example of the concept of significant figures. Let's say you're driving your car, and let's say you drove a total of 273.0 miles on a fill-up of 14.1 gallons. So if you want to find the mileage, of course, you'll pull out your calculator and you do this calculation where you divide the number of miles by the volume of gallons, and this is what you're going to end up with on your calculator display. However, you cannot just look at this number here and basically trust that your car will go on a gallon of gas to the nearest 0.000, how many zeros, and then 1 mile, or 1/100th of an inch, all right? What that means basically, therefore, is that some of these digits are meaningless, right? In other words, you have to drop some of these digits in order for you to get a value which correctly reflects the level of precision of your calculation. And that's where the significant figures concept comes into play. So let's talk about what we mean by the term significant figures. The significant figures in a measured value is a number of digits that are known plus one estimated digit, and that is considered as significant in a measured quantity, right? So if you're given a number, then which represents a measured quantity, then the number of digits that are known in that value plus one estimated digit would give you the total number of significant figures that are present, and which will reflect the level of precision in that number, all right? So let's say you're given this number, which represents some sort of measurement. Could be a measurement of length or time or whatever, doesn't matter. Then basically what we can say is that we are certain about the first 5 digits, the 5, the 1, the 6, the 1, and the 4. But what we are not certain about is the very last digit, because that digit is obtained by estimating it. And the level of estimation in terms of the number of significant figures is basically based on the type of instrument and the kind of scale that is used to obtain the measurement. And we're going to see an example of that shortly. In fact, here's the example right now. So let's say you are given a thermometer to take certain measurements, right? And we have these 3 measurements here for A, B, and C thermometers, right? Now you'll notice that in terms of the scale that is etched on the stem of the thermometer, these 2 have similar scales, right? While the third one is a bit more, a bit more precise in that not only do you have the same divisions as we have on the previous 2, where after 20 you have you have 10 equal divisions between 20 and 30. So that means that each of these divisions represents 1 degree. In this case here, you have smaller divisions between the 20 and the 21. So therefore, you'd expect to get more significant digits when you read off your value based on the scale. So as you can see, we have the mercury present in the thermometer. And what we're going to do is go through the exercise of determining the temperature based on the mercury level compared against the scale that is provided here. And here's where you're going to see how we get the actual number of significant figures represented. So in each case, so in the case of A, we have, let me back up a bit here. Okay, what am I doing? Okay, so as I said before, there are 10 equal divisions between 20 and 30, which means that each division represents 1 degree. So therefore, the mercury level is above the 21 mark, right? So therefore, we know that the temperature being recorded here, or being represented here, is going to be 21 point something. So the question now becomes, what is that something? What is that digit that follows the decimal point, which follows the 1 in 21? So basically, based on the scale here, we have to, do an estimation. So one person could reasonably look at this and say, this is 21.1 degrees Celsius. Another person could say, well, this looks like 21.2. As far as I'm concerned, both persons are correct, right? Because what both persons have done correctly is that they identified with certainty the first two digits, the 2 and the 1 in 21. And then that person would have to estimate the digit after the decimal point, because there are no final graduation marks between 21 and 22. So one person could say 21.2, one person could say 21.1. The actual answer here is 21.2. But as I said before, if somebody said 21.1, if I were to grade that, I would give that person the same credit as the person who says 21.2, right? So therefore, the number of significant digits that we have obtained by recording the temperature represented here would be 3 significant digits. The first 2 would be estimated, the 2 and the 1, and the 2 after the decimal point would be the estimated digit, all right? So therefore, the answer here would be 21.2, or it could be 21.1, and the total number of significant digits represented here is 3. Okay, so that's what the measured value here for the temperature is for the first thermometer. Now for the second thermometer, you'll notice that the mercury level gets up to this mark right here. So this is 21, so that obviously means that this is 22, I'm sorry, right? So we know that it's 22 point something. Now the question is, what would be the digit after the decimal point? Because you must have a digit after the decimal point to get the correct level of precision, because after all, the scale that we have here is the same as the scale that we have in the previous example here. So therefore, the temperature here, we would record this as being equal to 22.0, because it seems as if the mercury level is exactly on the 22 mark, right? So basically, the temperature being represented here, would be 22.0, all right? And again, it would be 3 significant figures being represented here, all right? So the point I'm making, comparing these first two here, is that the level of precision pretty much must be the same in terms of the digit that is estimated after the decimal point, because they both have the same kind of scale. Now, let's look at this scale here, which, as I said before, is a bit more precise, because you have, in addition to the unit spacing here, 21, 22, 23, you have 10 equal divisions between 20 and 21, and the same between 21 and 22, and so on, right? So the question now becomes, what is the temperature being represented on this scale here based on where the mercury level is? So if you look at this closely, you'll know that, well, the temperature being represented here must have 22 point something, right? Because this is the 22 mark, and the mercury level is above the 22 mark. In fact, it seems as if the mercury level is just above the 0.1 mark after the 22. So we know that the temperature is 22.1 something, right? Now the question is, what is that other digit after the 1, all right? And one could estimate it. In fact, by my estimation, I would say that this is 21.11, but another person could reasonably say this is 21.12, all right? So basically, in this case, the answer is 22.11, not 21, I'm sorry. So this could be 22.11 or 22.12. The actual temperature here is 22.11. And as you can see here, the number of significant digits being expressed here is 4 significant digits, because the first 3 digits, the 2, and the 1 after the decimal point, those are digits that we're certain about. But the 1 after the first one here, the 1 which occupies the second decimal place, that one is an estimated digit, all right? So as you can see, when comparing these 3 readings, you can see that the level of precision as reflected in the number of significant figures is based on, in this case, the type of scale that is used to make these measurements, all right? And this is something that you'll see when you're doing experiments and you have to, let's say, measure temperature or measure volumes. You'll have to make these kinds of estimations to get your measurements recorded or expressed to the correct number of significant digits. Okay, so what we're going to get into next is looking at the different rules for determining the number of significant digits in a measured value. So what we're talking about here is a situation where, let's say you're given a measured value in a question. Then you have to determine the total number of significant digits represented here in that number. And that's important, as you're going to see later on, because you have to take that into account when you're doing calculations and rounding off your answer to the correct number of significant digits after you have done your calculation. So that's for later on. But for now, we're going to look at how do we determine the number of significant digits in a measured value. Okay, so this is the first rule, right? All non-zero numbers in a measured value, all non-zero digits are significant. So it doesn't matter what the numbers are, as long as they're not zero, they're significant. So in this example, you're given 461. What we have here are 3 significant digits being represented here. All right. The next example is, or the next rule has to do with zeros. And in fact, all the rules that we're going to look at from here on have to do with zeros in particular situations. So this rule says a zero is significant when it is sandwiched between non-zero digits, right? Such as this example here. Excuse me, 401. As you can see here, you have a 0 here, which is sandwiched between the 4 and 1. So that is basically 3 significant digits, because this 0 is significant in addition to the 4 and the 1. All right? And let me just say that it doesn't matter how many zeros that you have that are sandwiched between non-zero digits, such as in this example right here, 93.006. These 2 zeros are sandwiched between the 3 and the 6. So therefore, these zeros are significant, and therefore the total number of significant digits represented here is 5. All right? So that is a rule that deals with zeros in particular, a particular situation where it is sandwiched between non-zero digits. Here's another example, 9.03. The 0 here is sandwiched between the 9 and the 3, so the 0 is significant. Okay, the next rule has to do with zeros at the end of a number that includes a decimal point. And according to this rule, such zeros are significant. So if you have a number where you have zeros at the end of the number and there's a decimal point anywhere in that number, then those zeros are significant, such as this number right here, excuse me, 55.000. These zeros are significant because they're at the end of the number and there's a decimal point in that number, right? So the total number of significant digits here would be 5. Here's another example. In this example, we have 1 0 at the end of this number. Here's a decimal point. So that 0 is significant, and therefore the total number of significant digits here is 5. Okay, now here's a situation where a 0 is not significant. A 0 is not significant when it is before the first non-zero digit. So if you have a number such as this one here, where you have zeros, and then the first non-zero digit is comes after the zeros, then those zeros are not significant, and therefore this is only one significant figure being represented here. All right. Here's another example. In this case here, we have 2 types of zeros. We have this 0, which comes before the first non-zero digit, and we have this 0, which is sandwiched between the 7 and the 9. So this 0 is not significant, but this 0 is, and therefore the total number of significant digits here reflected would be 3. Okay, here's another situation where a 0 is not significant. A 0 is not significant when it is at the end of a number without a decimal point. And here is an example of that. As you can see, we have 4 zeros at the end of this number. There are no decimal points anywhere in this number, so therefore the 5 is the only significant digit here. All right. Here's another example. Now in this case here, we have a 0 at the end of a number here, no decimal point, and therefore the only significant digits are the first 4. All right, so there are 4 significant digits reflected in this number. Okay, so that's basically the rules for determining the number of significant figures. Now at this juncture, I want to make a distinction between 2 types of numbers that you will encounter in any problem in chemistry and pretty much any scientific problem. You have 2 types of numbers. You have what are known as the measured numbers, which obviously means these are numbers that you obtain from measurements. And the thing about these numbers is that these numbers have a finite number of significant figures. So if you measure something, you know, volume, length, time, whatever, that number has a finite number of significant figures, all right? That is true for every measured number. But there's another type of number that you will meet in sciences and in chemistry. And these are called defined numbers or counting numbers and counting numbers, right? We call them collectively exact numbers, right? So let me write this down here. Defined or counting numbers are known as exact numbers. So let me just do this here. So these numbers, defined and counting numbers, they are known as exact numbers, right? And the thing about exact numbers is that they have a finite number, an infinite number of significant figures, all right? So just to give you some examples of exact numbers, the number of people, let's say, in a classroom, all right, 14, right? That is a number that you obtain not by measuring anything, but by simply counting the number of people or students in a class, right? So that number is an exact number, and therefore it has an infinite number of significant figures. Here's another example of an exact number or numbers. The relationship between the meter unit and the kilometer unit, right? 1,000 meters is equal to 1 kilometers by definition, right? So these numbers are obtained by definition. So therefore, they are exact numbers and they represent, and they have an infinite number of significant figures. Here's a third example, the number of beakers, 7, right? Again, as in the case of the first example, we obtained this number by counting. We did not measure it using an instrument. So therefore, the 7 here in this example will be an exact number. And what you're going to find is that in future problem-solving exercises, you have to be able to tell the difference between an exact number and an inexact number or a measured number, all right? Because that will become important in terms of expressing your final answer to the correct number of significant figures, all right? So as stated here, the 14, the 1,001, and 7 in these examples are exact numbers, all right? And as a result, they're considered to have an infinite number of significant figures. So I would say that the key takeaway from what we have just discussed here is that the difference between measured numbers and exact numbers is that the measured numbers are obtained by measuring, you know, could be volume, could be time. You have to use an instrument to carry out those measurements. But the exact numbers, you do not have to use an instrument. Basically, it's either by counting the number of items, number of students in a class, number of beakers, or by definition, the relationship between the meter unit and the kilometer unit, all right? So that's basically what we mean by exact numbers. Okay, we're going to stop here. And the next topic we're going to discuss is how do we deal with significant figures in calculations, all right? Until next time.